Alright, today we're going to be talking about refraction, dispersion, and Snell's law. When I first learned these topics, my teacher gave me a hand-wavy definition and said, "Oh, don't worry about it." And I don't think I fully understood the principles behind these phenomena. So I'm going to do my best today to give you a little bit of background knowledge, maybe a little bit more context than you need for your VCE, but hopefully it adds to your understanding rather than detracts from it. So we'll start off with an analogy, and the analogy I like most is that of a car. And if you have a car that's riding up to some imaginary boundary, maybe this is just air and this is water, and later on we'll see that this could be glass, but you don't see cars driving through glass that often. And from the car's perspective, if its front right wheel hits the water first, it's going to slow down and the rest of the tires will still be at their original faster speed, and this will rotate the car so that when it's fully in the water, it might be on some different angle. And it's actually very similar for light waves. So if you see these waves coming in on about a 45-degree angle, this left-hand side of the wave is going to hit the glass first and turn the whole thing inwards. And so what you'll get, if I trace a ray through this, is it comes in on one angle and out the other. And as in our last video, we can't do any sort of analysis without a normal line. So remember we talked about one thing that this light ray could do when it gets to the boundary is reflect. And in this case, we would have that θ1 on the way in, the incident ray, and on the way out, the reflected ray. This angle θ is the same. But the other thing that the light ray could do is refract, which means bend. And we'll get a θ2 on this side. And the relationship between these angles actually has to do with the material properties of the two mediums. So I'll call this N1 and I'll call this N2. N is actually a ratio between c, the speed of light in a vacuum, and v, the speed of light in this particular medium. It's also a measure of how hard it is for light to get through this material, because say this is a piece of glass, there's going to be some electrons in this material, and so as the light is coming through, it's going to be picking up some electrical interactions from all of these electrons, and they will either slow it down or speed it up, depending on its speed before it came into the glass. So I'm sick of physics teachers saying it's because glass is heavier than air. It has nothing to do with the glass's mass. It has to do with how easy it is for this light to pass through the electrons in the glass. And now that that definition's out of the way, let's get to the equation that relates these two, which is N1 sine θ1 is N2 sine θ2. And this is something called Snell's law. It's very handy for describing interactions of light at a boundary between two materials. So why have I got a picture of some man in a pool that looks like his head isn't above his body? Well, this is a very fine example of refraction. And we're going to do a little bit of analysis with some numbers that I just made up, but we'll see why this picture is actually plausible. So imagine you're the person taking this picture. You're happy because you're doing physics. And in this example, I'll actually work backwards. We know that light doesn't come out of your eyes up to objects, it comes from the object into your eyes. But just for our purposes, I'm going to start by drawing the ray out of your head. Now remember, we need to put in a normal line to the boundary, and this is θ1. And we know that glass has a refractive index, N is about 1.5. By the way, the refractive index of air is 1. And let's pretend that θ1 is 45 degrees. And I want to find the angle that this light is going to exit the glass and air boundary on theta 2, which, by the way, because of geometry and parallel lines, it's going to be the same as the angle that it enters the glass water boundary on. So we're looking for theta 2. So our governing equation is this: n1 sine theta 1 is n2 sine theta 2. And since we're solving for theta 2, I'm going to work from the outside in and divide both sides by n2. n1 sine theta 1 over n2 equals sine theta 2. And what's the opposite of sine of theta? Well, it's sine inverse of theta. And what I do to one side, I have to do to both sides. Sine inverse and sine cancel, so I will have theta 2 is this expression on the left. Now that I've solved for theta 2, I can put in my values. Theta 2 is sine inverse of, what was n1? It was just 1 because the first material is air. Sine theta 1 was sine of 45 degrees. And n2 is 1.5. Now remember, when you put this into your calculator, you have to take the entire thing, including the divided by 1.5, the denominator, as part of your inverse sine. And the number that you'll get is about 28 degrees. So you'll see that actually theta 2 is less than theta 1. In other words, the light, when it hits this boundary, is going to bend towards the direction of the normal line. Now let's analyze what happens when light meets the glass water boundary. And water has a refractive index of about 1.3. Well, I'm hoping that the light is going to bend and hit our friend in the pool there. And this would be known as theta 3 in there. So in the exact same manner, I can solve for theta 3. And if I put my units in now, I'm using n2 sine theta 2 over n3, which is sine inverse of what? n2 was 1.5, theta 2 was 28 degrees, and n3 is 1.3. When I put this into my calculator, I get about 33 degrees. So what's actually happened here, because it is easier for light to travel through water than glass, the light bends away from the normal line. How is that possible? Well, if we come back to our car, imagine now that our car is traveling the other way, and our front right tire is going to come out of the water first, and that'll be moving more quickly, so we can turn our whole car away from the normal line, which would have been here. So that's why this interaction between the glass and water, even though I haven't drawn it to scale, we can at least see that it's plausible. And this leads to another phenomenon, which is called the dispersion of light. So we know, thanks to Isaac Newton, that white light is a combination of all of the other visible wavelengths. Now, this is the part that I said my physics teacher gave me a hand-wavy definition on why every wavelength of light has a slightly different refractive index. The angle that it makes when we come to this boundary, if this is theta 1 and this is theta 2, those angles are all going to be slightly different, as you can see here. If that's enough for you, fine. Feel free to stop the video now. But it wasn't enough for me during my year 12, and I wish that I had a better understanding of why this phenomenon occurs. But the proof that I'm about to do isn't something that you need to replicate or even understand for your year 12. It's just something to add to your understanding. So remember before that n was a ratio of the speed of light in a vacuum over its current speed. But remember that v equals f lambda, the frequency times the wavelength that we see. But n also relates to the material properties of the medium that the light's traveling through, and it relates to these two numbers epsilon r and me r, which stand for the relative permittivity and permeability of the substance. What does that mean? It doesn't matter for our purposes, but it's basically a measure of the electric field within the material. Well, the speed of light, c, is also made up of some constants. C is 1 over the square root of me naught, epsilon relative. So if I make this substitution now, I have 1 on f lambda root mu naught epsilon r epsilon o is root epsilon r me r. And what you'll see here is that epsilon and epsilon cancel out. And if I solve for the wavelength, I get lambda is 1 over f root epsilon naught mu naught, and I'll write this mu relative separately. Now the beauty of this is that these three are constants. So we'll learn in our upcoming area of study that the energy of light equals hf, and because of the conservation of energy, our frequency can't change. So f here is just a constant, or we can write that lambda is proportional to 1 over square root of mu relative. What does this mean? Well, if I change the wavelength, how do I change wavelength? I just change color. I look at it red instead of blue. If I change the wavelength, this is the same thing as if I slightly changed the material property of the glass. So this is a bit of a mathematical proof of that idea. Once again, you don't need to know that for your VCE, but I think it might add to your understanding a little bit. So thank you for watching this video, and remember you can email us at any time with your STEM related questions using the email in the description.